Let's start. Okay, the first speaker in the session after the coffee break, and I hope that this audience online also had a coffee. Yeah, is Dr. Omololu AKIN-OJO from ICTP, the East Africa Institute for Fundamental Research. And maybe it's also important to note that as part of the MOU between NITheCS and ICTP, also the East African Institute for Fundamental Research is part of that agreement. Yeah. So please, Omololu, if you would like to start with your presentation, you're welcome to go ahead.
Okay. Thank you very much, Francesco. Thank you for the organizers for inviting me. This is I'm very appreciative of this, so thank you very much. I'm sorry I could not be there in South Africa. Unfortunately, I had some visa issues, which would have taken me some more time to resolve. So I thank the organizers for providing this opportunity to share online what we're doing in this part of Africa. And of course, I would like to thank the other speakers also, because they've highlighted some of the things that we know in Africa, or some of the challenges we have in Africa, and some of the things that are happening in the area of technology, especially surrounding AI and machine learning. So again, my name is Omololu AKIN-OJO. I'm the director of the ICTP East African Institute for Fundamental Research. It's a UNESCO Category 2 institute, and it was set up by the government of Rwanda in collaboration with the Abdusalam International Center for Theoretical Physics, of which the director, Professor Atish, DABHOLKAR, is visiting with you, and he has told you many things about ICTP. So this institute was set up by the government of Rwanda, in collaboration with ICTP in Italy and the University of Rwanda. Our focus is science for African development. And so what I'm going to talk to you today about is about HPC, which you know what the acronym means, and African CRAM. So I'll tell you what CRAM means in the next slide. The full title is High Performance Computing in an African Collaborative Research in Atomistic Molecular Modeling. So we created this group called Collaborative Research in Atomistic Molecular Modeling, or CRAM for short. Basically, we are online. We meet online 1 to 3 times per week. Actually, we meet I come on 3 times every week, but other participants only need to come on like once a week. So we meet Monday, Tuesday, and Wednesday, 1 to 2 p.m. every day. And we try to just restrict our meetings to 1 hour, because we know we'll meet tomorrow or we'll meet next week. Where are the people from? They're from different parts of Africa. Of course, I'd like to say we are from all parts of Africa, but unfortunately not. Some people, so these are the names of the people that we are working on, and there are other people that have not listed their names, but you'll see how they're connected with us. So some people are from one part of Africa, but they're working in another part of Africa. So namely, for instance, myself, I'm from Nigeria, but I'm working in Rwanda. And Musa Hussein is from Sudan, but he's working in South Africa. And so we have this collaboration online. And we are from different parts of Africa. So later on, you'll see one of our desires, and I will explain to you what we are doing. Actually, what I wanted to do first was to tell you our goals, and then I'll talk to you about our computational research. So our goals is actually to first to provide training in research. So the goal of this CRAM, which is also related to the goal of the institute, is to provide training in research. So one of the things we found is that African, especially young people, are eager to do research. But unfortunately, some of us, we do research that's outdated. So some things have already been solved, some problems have been solved, and they're not interesting. But some Africans are still working on it, either because they don't know, they don't have access to papers or different things. So of course, so we want to help them to be able to choose good research, and then train them to do high quality research. So this is one of the goals of this CRAM. So we want to train them to do high quality research. Since we've been working together and writing papers, I've noticed different lapses in different people, and we are working together to get training in research. Especially also because there are different people from different parts of Africa, and standards are slightly different, but we are coming together to build something that will be of international standards. So everybody is receiving some training in this respect. Of course, we want to have joint discoveries and have joint research together. This is separate from training in research, because let's say we are already excellent, everybody is excellent, then we could just say we come together to do joint discoveries and research. Okay, but this is not the case. We need to train ourselves, okay, and then at the same time use our training to for joint discoveries and research. I'll tell you some of this later on. And of course, the other thing is, the final thing is, we are coming together to share resources. We are coming together to be able to share computational resources, both hardware and software. The software, one goal was to say if there was a software that was proprietary, and if one of us acquires it, then the person could share it with all of us. But unfortunately, it has not worked that way for us. We have mostly been using open source software, so we didn't have much sharing of computational resource, sharing of software, because could have well have downloaded it without the group. But we share computational resources in terms of hardware. We also come together to share information. So the different information on conferences, on open positions that we share together. And finally, we share resources of human expertise. A simple example is that I have some collaborators in Europe and in the US, and sometimes we encounter a hitch in our research, and I share the human expertise resource that I have. I share it with the group. What does that mean is that I contact these people in Europe and ask them, okay, how do you get this done? I try this, it doesn't work, and then some of them will tell me, okay, you should do this and do this and do this, and then I share it with the group. So this is part of the way that we share our human expertise. And also, you won't believe it, some of the other people that we worked with together in the group, they have other expertise. There's one guy who started working with us in machine learning, and he became very good, like super expert, like just knows a lot, and he helps the group when we are working in the areas of machine learning. Okay, I'll come back to this now to tell you about our computational resources. So, of course, this is Africa, giant Africa. And in this little part of Africa, where Rwanda is, this is where we are located. And it's tiny, but it's like the heart of Africa. And we have a small cluster, it's just 4 nodes. Okay. This is the cluster, is exactly level 5. I'm on level 3 now, it's exactly on level 5. It works. Rwanda is cool enough, so most of the time we don't need air conditioning for it, but we're trying to get some air conditioning for it. I don't even have a KVM switch, as you'll see, so I just, if I need to check this node, I disconnect from here and I check, okay. But believe me, this thing is functional, and many people are logged into it from Ethiopia, from Tunisia, from Cameroon, from Nigeria, logging into it and doing work. So this cluster we call TWAS1 because we got a grant of $25,000 from TWAS, the World Academy of Science, to buy this cluster. We also have a smaller cluster which we got before from ICTP, International Center for Theoretical Physics. It's not housed here, it's housed in ICTP. And of course, we have access to this cluster we call Qubits, and it has 80 processors and could run 160 threads. The TWAS1 has 160 processors and could run 320 threads. Chineke is this, we have an account which was given to us through ICTP. So ICTP has an MOU with an agreement with Chineke, and they were able to give us 2022, they were able to give us 2.5 million core hours. Of course, we used it up, and then they increased it thanks to Dr. Ivan Giroto, who I think some of you have met. He helped us, so they increased it to 3 million core hours, then 3.5, and now 4 million core hours. And I put a plus because we're able to use some low priority queue, which really actually works, especially during the weekends. We're able to use it and run our jobs on it. So it's kind of running low priority. It's not charging us anything, although it's charging them energy to run it. So these are the facilities we have, and we make it available to different people. So now I'm going to tell you some of the work we are doing. The work we are doing is mostly in these areas that I've listed: molecular dynamics with a software called LAMPS, which, as you know, is open source. GROMACS, also open source, and ASC. We do some electronic structure also. Well, not some, actually a lot of electronic structure using Quantum Espresso and OCA. Unfortunately, we don't use VASP because it's proprietary, but we use Quantum Espresso and OCA. OCA is a quantum chemistry code. So also we don't use Gaussian because we don't have access to it, but we're able to use OCA, which more or less works similar. The input is similar to Gaussian for the most part. Quantum Espresso, because we use Quantum Espresso and not VASP, you really have to have some expertise in command line and working with command line to use Quantum Espresso, which there's some program that we have called Assessment that teaches students, and we also teach some people how to. Then about a year ago, we got into machine learning, and we mainly use scikit-learn with a little bit of TensorFlow to build some machine learning potential. So what we really do in electronic structure is what I've shown in this slide. In electronic structure and molecular dynamics, because I won't talk too much about them. Mostly I will talk about what we're doing in machine learning. In electronic structure and molecular dynamics, basically you take a structure and you solve Schrodinger's equation, and this involves a lot of effort to solve it. So this is an important place where we need and we use high performance computing. So currently now I'm actually running a job with, those of you that I know, with hybrid exchange correlation functional in density functional theory called HSC, and it's very compute intensive. Okay, so but all that is just to solve this equation, H psi equals H psi, Schrodinger's equation, and then we do some post-processing. You post-process, and then you can get different properties of this crystal, for instance. In this case, I give an example of zinc sulfide. You can calculate the electrical conductivity, the density, thermal conductivity, magnetism, magnetic properties, whether it's a piezo or ferroelectric material, optical properties, and many other properties. The good thing, of course, with computing as compared to experiment is you do all this with just one piece of it. Okay, so it's just your computer. If you were doing experiments, you have to use different apparatus for each of this. Electrical conductivity, you have to use like a 4-probe device to do that. Density, of course, is simple to measure. Thermal conductivity, also magnetism. You have to use different equipment for doing that. So this is one of the advantages we have in computational methods, that we can do this relatively cheaply in Africa. I mean, we don't have yet $250,000 to buy an SEM machine, but you can buy your laptop and then can acquire some machine like this one for $25,000. So it's a tenth of the $250,000 that you need at least for an SEM machine. Okay, so this is basically what is done in electronic structure and molecular dynamics, and different variants of this. Okay, but I won't be talking much about this. We do this, but I won't be majoring on this. This is an example of a work that was done by Steve Jonathan. He's from Central African Republic. So he asked to use our cluster. He was doing some work on docking of an anti-cancer drug. And so he had been doing the work before on some other clusters. And then he asked us that, oh, he needed some computer time to finish the work. So we allowed, and so he acknowledged us here, which is an acknowledgement we are happy to receive. So he studied the drug the drug alone in vacuum using computational chemistry methods. And also he docked the drug into some proteins associated with different cancers. So one of the cancers was prostate cancer, another one was lung cancer, another one was breast cancer. So he did the molecular dynamics, or part of the molecular dynamics, using clusters here. This was one cluster, that cluster you saw, just followed. Okay. So here's another example of work we are doing. In this case, these are the authors. My name is not there yet, but I'll add it. And we are predicting the nature of semiconductor band gaps using machine learning techniques. So band gap for different materials is there's a gap, energy gap in different materials that the constituent electrons don't have energy within that energy gap. So that's why they call it an energy gap. Within that gap, so they can have energies up to like 4 electron volts, and maybe after that 6 electron volts. But between 4 and 6, for instance, there's no energy. I mean, there's no electron with an energy between 4 and 6. That region is not allowed. Okay, so, but that is not even the most interesting thing. The thing we're working on in this case. What we're working on in this case is that there are 2 classes of materials that have a band gap. One is materials whose band gap are said to be direct. Another is a set of materials whose band gap are said to be indirect. Okay. If you are in physics or a little bit of chemistry, then you understand what these structures are. But if you are not, just know that there are 2 classes. So there are semiconductors or insulators, and there are 2 classes of them. One is we call direct, and the other we call indirect. Okay, I won't go into details of this. So of course, this is a good problem that one can use machine learning classification methods to try to solve to direct and indirect band gap materials. Of course, you can use quantum espresso and ab initio methods to calculate the structure, and people have done that to calculate the structure of different compounds. Like I've shown here, you can calculate the different compounds, use this to get the band gap, and determine whether it's direct or indirect. One can do this, but it takes a lot of time. So if you have like 300,000 compounds, you don't want to do this ab initio calculation for each of them. People have done this kind of calculation for like up to 10,000 compounds, or even over time, people have done it for like 30,000 compounds and even 60,000, 100,000 compounds. But it takes a lot of time and a lot of effort. So what we wanted to do was to see if we could use machine learning to quickly and easily predict whether a material was a direct band gap material or indirect band gap material. How did you do this? So if you take the crystal, what we did was what we call featurization. You take the crystal of the material, and then for each atom, there's different properties. Each atom has the ionization potential. It has an average atomic mass. It has a certain number of valence electrons. So you try to find these properties for the whole crystal, not for just one atom, but for this whole crystal. So for instance, for this whole crystal, you can find the range of the atomic IPs. So zinc has an atomic ionization potential, sulfur has one. So the range will be the difference between that. So this is one of the properties that we hope that can help with our classification. So it would be very good if materials that have a range of atomic IPs, atomic ionization potentials are direct band gap. Those that don't are indirect band gap. As simple as this classification could be, you wouldn't believe that there's no theory that actually predicts and is able to predict without a lot of calculation whether a material will be direct or indirect. You really have to do the calculations. It's not like when I use sodium and chlorine and you already know that one is going to be ionic because sodium has 1 extra electron, and chlorine needs 1 extra electron. And so you know there'll be transfer of electrons and it will be ionic. Okay. We hope that there's such a simple thing that one could use to say that a material, this will be direct or this will be direct. For instance, in one dimension, one could easily say that, this material will be semiconductor or metallic. You just have to know whether the number of electrons is even or odd. So in one dimension, you can know whether it's metallic or not. So we are hoping to find a simple way like that to be able to tell whether this material is direct band gap or indirect. So anyway, we take the crystal and we calculate simple properties of the crystal from the atomic properties. And then those properties are what we use as our descriptors. And we try to use it to sort the structures based on, we try to sort the compounds based on these properties. So I'll just show you the results. So we use a method called random forest. I won't go into details to describe the random forest, but what we did, so we use random forest, and there's a library you use, but the details of it, you will actually create trees, and you use an ensemble of those trees to make decisions, which will decide whether material is whether the material is direct or indirect based on the simple properties that we have listed here. Okay. So this is the result of what we did. So this is the result of what we did. So 42% of the materials are actually indirect, and were predicted to be indirect by our model. 8% are actually predicted wrongly by our model, and 41% are direct and predicted correctly by our model to be direct, and then another 8% are wrongly predicted by our model. Okay. So the challenges we have, of course, for the machine learning, we have 30 compounds from a DFT database. The featureization actually takes some time. Developing the machine learning model also takes some time. The one that takes the most time is the hyperparameter tuning. So if you're somebody that uses machine learning, you know what that means. And one of the things that helps is to use many cores. And so this is just one line of the code. And if you just put n jobs x32, then you use 32 cores at once. Okay. So this is our simple example of using high performance computing. Of course, if we also plan to use DFT calculation to check some of our results, but this will take a lot of time. And we also want to make prediction for data that is up to like 18 gig. So these are some of the challenges we have there. We're also trying to use machine learning to predict whether a material is metallic or insulators. For one dimension is simple. For three-dimensional materials, then there's some challenges, but it seems to be working well. So this is some of the things we're doing in the group. I'll tell you some of the challenges we have on a practical basis. One of them is the low expertise of users. Okay. For instance, we have users who are doing their jobs and they're writing scratch files to home. And then the disk gets filled up or is slowing down other people. So there are people that have low Linux expertise, okay, and we need to train them for this. The other thing is just because your job runs does not mean you're running it correctly. So like I said, your job could be running, but you could be writing to home instead of writing to scratch. The other thing I notice is users are typically, some of them are not able to compile their binaries, okay, or create efficient binaries, okay. I was in the situation like that also in the past, but then I learned some things. I learned some libraries are faster than other ones. For us so far now, we have 0 GPU coding expertise. So with GPUs, we know nothing about that. Of course, we would like to increase our HPC power, both the memory and the CPU power. This power is not so much a problem. And then the final thing is we would like to reach more researchers in Africa to give them this opportunity to work together, train them in different things that we do. So I'd like to end by saying thank you, Omurakoze, Asante Sana. Thank you very much.
Thank you very much for the great talk. Thank you. And